And so I will speak about our joint work with Vladimir. So that relates weight structures with localizations of categories. So you certainly know very well what is the localization. In general, you have some category, and you want to make some morphisms in it invertible. So if it's if objects of A form not a set but a class, there could be some set terrific difficulties, but we will ignore this during this talk. This is really not important. Okay, so there is a universal construction, maybe to Gabriel and Sisman. And so in this localization, so this universal construction, the morphisms are so-called zigzags. So you should consider chains of formal compositions like this, and this chain can be arbitrarily long. And so in general, this is the morphisms in the localization are quite nasty. And the question is when we can improve it. So the first case we can, a well-known case when one can improve this is when we have the first order condition. That just means that we have a long zigzag, we can make it just convert it into a fraction. If you have either the left order condition or the right first order condition, then they will have one fraction. Maybe we will divide from another side if we choose another order condition. And in particular, this condition is fulfilled when we localize triangulated categories. So there is certainly a very nice theory of Verdier localizations. And I was really surprised that actually the situation is not much worse when we localize additive categories. So it seems that experts more or less know. Okay, so we proved it. Okay, there are before this there existed some somewhat weaker result, but I would say that to a non-expert in this field, it's quite difficult to understand what happened in this field. Okay, so the first result that is known to the experts is the following one. So under some natural condition on S, the localization will be so the abstract localization like this will be additive. And as a corollary, so this can be proved by some extra nonsense argument. Yes, so that's to experts this to be well known, but yes, not. It was not written down in any book, at least in some preprints only. And this means that for arbitrary S, you can should just extend S so that it will contain all identity morphisms and will be close to direct sum. And when you localize by this extended S, you also obtain an additive category. So for any S, there is a universal additive localization, additive version of the localization. And the first result that we original result is this one. So it is can be formulated without weight structures that will appear just a little later. So the localizations can be so in order to calculate the additive localization of A, you should consider the Verdier localization of the gamma-topic category of complexes over A by columns of morphisms of S. And inside, you consider those objects that come from A itself. and this will be the universal additive localization of A by S. And also there are some methods and formulas for computing the morphism groups in this localization. So these formulas will appear in this talk a little later. Okay, so this so it exists, but it is also more or less effectively computable. Now, so it's so there are so to my surprise, people usually didn't consider localizations of additive categories, but instead of this, they certainly considered localizations of rings of rather general sort, and certainly these two problems are closely related. So this is called non-commutative localizations. Certainly, all of you know that the classical results in this direction, so you can localize your ring by a set of morphisms if your ring is either commutative or maybe or it's sufficient for us to satisfy the ORA conditions, two of them, either left or right. This is and certainly this result also can be extended to additive categories. Okay, so this is well known. So less well known activity is so-called non-commutative localizations of rings. So suppose that the ORA condition is not fulfilled. Then it turns out that it's more natural to consider not only elements of R, but also matrices over R. And so a generalization of this setting when you invert just elements of R is that you consider some matrices over R, finite matrices. Or more generally, you can consider morphisms of finitely generated projective models over R. And the question is to construct a commorphism that will make all these matrices morphisms. Okay, it's easier to understand what all these morphisms invertible after the change of coefficients along this homomorphism. Okay, so now explain this is really how this reduces to localizations to additive categories. This is certainly very easy. So we consider either finitely generated free modules over R, or more generally finitely generated projective R modules. Then R considered as a module itself is a generator, or maybe generator up to the direct summons. So it's called Karoubi closure. I will say about this a little later. So when you consider the localization with respect to corresponding morphisms, we obtain that this category is also generated by the image of R. Как красиво по-английски? Script R in this category, or you may say this is just the same object R script. So we obtain that so it's also a generator. So it means that the universal localization ring is just the endomorphism ring of this object in the localized category. So this localized category in the case of projective modules even contains a little more information than just this ring. And so there were several authors starting from Kohn that proved something about these non-commutative localizations. And certainly one can also argue in the converse direction. So if you have an arbitrary additive category, we can try to find a generator for it. But usually we don't have a generator, but we we have an int generator, I would say so. It's probably when I think that one can prove some statements by this method, but okay, I wouldn't say that this would be optimal. And I didn't check that you can really generalize everything, because we certainly went in the converse direction. Now about motives. So this is actually, I was never interested in this localization of rings. I was interested in motives, and one of the methods, one of the interesting motivic categories is the so-called category of birational motives. So Kahn and Sujata in their rather old preprint defined birational motives over a perfect field, and but this definition, so there is the definition is easy, so it can be easily generalized to a much more general to any base scheme. Okay, before so the idea that you should consider some of the definition that you should localize the category of effective geometric motives by cones of open dense embeddings. So everything depends on how you define effective geometric motives. I will, several times I will need the following technical definition. So if you have two subcategories of a category, they will always be additive. Then we can consider the relative corrobization. So this is the category of all retracts of objects of B inside of A. And there is also the absolute corrobization. This is the you can construct for any category the category of formal retracts of its objects. So this is technical. You can more or less ignore it, but just to make statements correct, sometimes you need it. Okay. So yes, suppose we have some base scheme U. How can we define effective geometric motives? One should start with some additive category of correspondences over U. And correspondences are some algebraic analogs of formal linear combinations of multivariate functions. So you want to, since you can compose multivariate functions, you obtain an additive category this way.
Silly question. What are objects of this category for you?
Yes, I would like to say that yes, there are some definitions of this type, maybe starting from Suslin. Okay, so there are some now there are some, for example, treatises of de Glies and Szynski with some definitions. But the point in my talk is that I don't need to choose a fixed definition. I just need some.
I asked not about the definition, I asked about just objects of the category.
Yeah, so I don't need to fix them also.
Okay, in this case, I will say my guess is objects are just
small schemes over U is the basic.
Yeah.
Is the basic.
Schemes, which are U schemes, so schemes together with Morrison to U, and this Morrison to U is smooth. This means that you consider smooth families over U, parameterized by U.
Yes, but actually, for example, so this is one of definitions used by de Glies and Szynski, but they also define some certain generalized motives. So to this end, they consider morphisms that are just of finite type and not necessarily smooth. And so for these definitions, you need some algebraic geometry to make it work. But you can consider also make some silly definitions that will work in any situation. Okay, so so I need some. I don't need much properties of this definition. So the objects of some schemes over U, yes, basically smooth, but maybe, and also need that smooth morphisms of schemes will give morphisms of U schemes will give morphisms in my categories. That's all I need in order to define. It actually suffices for Italian morphism of schemes to define. Morphism is my category. Then I can proceed with any choice of this additive category that satisfies these axioms. So you just consider bounded complexes, and you localize it by homotopy invariance and by Nisnevich. And okay, and then you can consider the groupizations, but this is not really important.
But important, I think, for you and for us, that category core, even if we don't know its definition, that it is an additive category.
Yes, certainly. Yes, this is the most important property. So what does it mean? Okay, so homotopy invariance, you force homotopy invariance for any object scheme such as the corresponding objects lies in our category. I take the complex, two-term complex like this, and for any distinguished Nisnevich distinguished square, I consider, so I do not define this Nisnevich distinguished square here. We just I only need a part of this definition. Okay, but so certainly the definition is easy and well known. So I want to. So I also localize by these complexes of this type.
For instance, take just cover of X by 2 Zariski open pieces.
Yes, sure. Yes, this is okay. Yes. So about this definition, so this is certainly very similar to the definition of Voevodsky. The main distinction that when the base is a perfect field, there is no need to localize by Nisnevich distinguished squares. It suffices to localize by ordinary Meyer-Vittorius. But for a general base, it seems that so then if you localize by ordinary Meyer-Vittorius, then you automatically localize by Nisnevich Meyer-Vittorius. In general, this seems no longer to be true. And since we want Nisnevich descent, it's better to take this definition. And the first one to give such a definition, I think, was Florian Ivora. Okay. Okay, so then, as I said, after we defined effective geodetic motifs, we just localize by cones of open dense embeddings between objects of our core U. Now, okay, so this is not a very complicated definition, but a trivial observation is that so in the Nisnevich distinguished square, yes, as I've said, the rows are open dense embeddings. It means that if we factorize by birational equivalencies, then we automatically localize by also by Nisnevich squares. So it implies that we don't have to think about Nisnevich squares at all in this definition. And after we forget about these squares, so we only localize by cones of morphisms. And so that means that we apply the result that I stated in the beginning of my talk. So we can apply. So this is really very important. This technique works only when we localize by two-term complexes. So it's absolutely catastrophic if you have longer complexes that cannot be reduced to term ones. This is certainly it's very easy to understand that everything goes wrong. But here everything is okay. So I will also, and we can apply the general theory and obtain some new results for birational motifs. So some remarks. The first remarks, the formulas will become certainly better if we note that we also need comotive invariance here. So when you localize by birational invariance, you automatically localize by comotive invariance. So this is can be proved by an argument due to Colliot-Thelen. And this remark was made by Bruno-Kahn.
Can you give some intuition why it is true?
So you should consider some multiply, I think, x by p1 cross pi1 cross pi1. This is some clever geometric argument, but it's not complicated. So some functoriality, you play with some surfaces and you obtain the result.
There is a general thesis due to Vygotsky, which says that there is a language and there are theorems and proofs. And thesis says that if you want to prove in scientific business a significant theorem, use geometry. This is
okay. So all of my results are not significant automatically. Okay. So yes, my point is that so what do we get without general theory? So without any geometry, we obtain. So we obtain some results for this category without using any geometry. So
this was my two questions. So it's written probably, and in the third in the item 3 it's written also possibly. So my question here are two questions. Is it done or it is an interesting question?
So the first observation, yes, I said that we can get different choices of core U. So the answers to your questions can certainly depend on the choice of core U. So certainly there is a choice as people are the most popular choice that generalize the one of Vygotsky, and so Bruno-Kahn told me that for this choice he can probably prove it. And I can prove some part of this result for this choice.
Let's consider the item number 3.
Oh, so yes, I want to explain this. So the point is, okay. The birational motifs are certainly closely related with effective geometric motifs. The problem is that when you consider motifs over a base that is not a perfect field, then we don't have the cancellation theorem. It means that the effective geometric motifs are not the best, are not the very nice, I would say so. It seems that people cannot prove very nice properties for them. And
still you don't have cancellation?
I think for when the base field is not perfect, I think we don't have. I'm not sure. Okay. So you obtain. So I obtain some result, but probably this category is not is less useful than in the case when the base is a perfect field. So this is the answer. And for example, so I will speak about weight structures now. And for example, it's more difficult, you would say, to produce interesting objects in this category, for which you would like to apply this theory. Okay, but maybe so if you can take some quite distinct choice of core U, and maybe it will make sense and for a very general base, this seems to be quite possible. Okay. I would say, okay, that now it's not everything is clear with these things. This is people work with them. Everything is in the beginning, more or less. Okay, so here is a basic definition that I gave in this room for several times. But now I will recall it to you.
May I ask you? I privately tried to ask you a couple times what is the motivation for definition of weight structure, and specifically I asked does it relate somehow this definition to definition of weight structures which is due to delene.
I would say that there is no definition of weight structures due to delene.
Something strange for me, because when Frobenius acts on cohomology of varieties over finite fields, then in cohomology we have weight structure.
So we have weight filtration for cohomology.
Weight filtration for cohomology,
Okay.
but not weight structure.
So nobody called this a weight structure, I believe. So this is always called a weight filtration. Yes. And I will say about the relation some words.
You will see something.
Yes.
Okay.
And certainly I can tell you everything privately for infinite amount of time. This is absolutely no problem. Okay, so I would say that weight filtration is from the very important distinction that weight filtration is usually not triangulated. Basically, is not a very much triangulated definition. There is some definition for triangulated in BBD, but it's Pelinson, Bernstein, Delene. But so there are some properties of weights, triangulated weights of BBD, but they are listed distinct from from this one. So there was no, they didn't make any attempt to axiomatize. So there are some properties, but no axiomatization. Okay, so this is very general definition for triangulated categories. So we choose inside some, you choose objects with non-negative weights and non-positive weights. And so for axioms, the first one is rather technical. So I would say that also the axioms are quite similar to the ones of T structures, but the result is really, you can say, surprisingly distinct. So the consequences. So you may say that you just change one axiom, significantly change one axiom, and you get something really new and interesting.
I definitely will give you a bit more time, but since I really want to understand, yeah. So suppose the category we look at is category of complexes of finite dimensional vector spaces over, I don't know, maybe finite over algebraic closure of finite field, but with action of Frobenius. So
okay, so representations of Kähler group? What is the category?
So I would like to...
So you try to do something with Frobenius. There is a, okay, I'm going to try to give you an answer, but I'm not sure that...
Maybe a simple example one should take in mind of such a category.
Okay, yes. So here is the example on the next page. So you just you can say that you just mimic the properties of steep truncations of complexes. So you consider a homotopy category of complexes over an additive category, and the weight decomposition of a complex is just given by steep truncation. And you find out, certainly you find out that if you choose another representative of your complex up to homotopy equivalence, then your steep truncation will change. Yeah, so, but still it turns out that this is not catastrophic and you can work with it and obtain quite interesting result even in this very simple case of complexes. So being honest, I also started with homotopy category of complexes, but these were complexes over twisted complexes over negative differential graded category. But you also have stupid truncations in this case. And a particular example was the Voevodsky category with motives. So everything started with motives, but so here is quite an easy example.
And in that case of category of motives, so motivic complexes, so could we comment on weight structure?
I hope and my talk you understand something. Okay, so you consider something of non-negative and a non-positive weight. So the Karoubi closed is so when you consider T structures, you want the positive and the negative part to be strict, close with respect to isomorphisms. And now you also and here, in order to obtain, you can say a rigid theory, you need also Karoubi to contain all retracts that are inside your C. Okay, this is technical. So the distinction with T structures is the one that is they behave counterintuitively with respect to shifts. So when you look at complexes, so you take the negative part is complexes that are concentrated and in positive degrees, and the ones that are homotopy equivalent to them. And the positive part is negative complexes, and those that are homotopy equivalent to them. This is so I had to make this choice because there are some categories of graded polarizable Hodge structures and also Hodge modules where there are weights compatible with that are part of case of my definition, but the conventions are always the counterintuitive choice of conventions.
So the category of mixed Hodge structures?
No, you need the triangulated category of graded polarizable. Mixed Hodge structure, mixed Hodge complexes. Maybe I.
This is an example of category to which one could apply.
Yes.
Your language.
Yes, this is correct. But so for if you without this graded polarizability, this is the orthogonality. If you just consider the DMHS, this orthogonality axiom would fail. So there would be natural candidates for these two parts, but we won't have orthogonality like this. And this is also the case with Galois representations. You also need some polarizability in order to have this orthogonality. Okay, yes. So the axioms, yes. So this is how they behave with respect to shifts, somewhat counterintuitively. And orthogonality means that there are no non-trivial morphisms from the negative part to the positive one. And lastly, that you can decompose any element into a negative and positive part, and as I've said, this decomposition is more or less never unique. So it just exists in contrast with the situation for T structures. And now we define the heart. The heart is just something, the objects of weight 0. And for Vygotsky motives, for the basic examples that I started with, so the heart will be the category of Chow motives inside Vygotsky motives. So I proclaim the Chow motives to be of weight 0. So technical definition of weight exact factors, certainly weight exact factor is something that preserves weights. Now some simple remarks. So in contrast to when you have a T structure, then you don't have, you only have more positive degree extensions between the objects of the heart. And here is the opposite, the situation is opposite, you only have negative extensions of non-positive degrees. And you may say this category is negative in C. Okay, so another observation is I said that filtrations are not canonical, but so there is some weak functoriality, maybe I will say it about it later, and it immediately implies that we can define weight filtration for any comotive theory. Actually, for any functor, yes, for any functor to an abelian category, yes, I didn't write that A is abelian, you can define its weight filtration. And also, I would like to say that to those who came from Moscow, and maybe to somebody else, that we obtain examples of weight structures from semi-orthogonal decompositions of triangulated categories, but this is very degenerate situation. In which the heart is 0, that, okay, this doesn't seem to be a very interesting example. So, and you can also obtain, as I've already said, from different negative differential graded categories.
Are there interesting examples for categories of sheaves? Like if you look at sheaves?
Certainly, okay, so for any additive A, as I've said, you can define a weight structure on the category of complexes. And usually when you have a derived category, if this is the equation, then it is either isomorphic to certain comotopic category of projective objects or comotopic category of complexes of adjective objects. And so you can define weight structure using these isomorphisms. And so there are also some, okay, if you have a large triangulated category, there are certain, you can try to generate a weight structure starting from some objects. But yes.
But there's no relation to geometry of if you have sheaves on X, there's no examples coming from geometry, for instance. Okay.
Another thing you can do, you can try to glue, so you can take weight structures, as I told you, coming from projective or adjective modules. Then you can try to take some pieces of X, and if you have gluing for triangulated categories, then you can try to glue. Then you can glue the glue weight structures. So yes, answer is okay. So there are some easy examples for which the answer is yes, and also maybe for more complicated. There could be more complicated and interesting examples, but I just didn't work on them. Yes, and so mixed Hodge modules, yes. There are some types of modules, you may say so. This is a really complicated example, yes, if you want it.
Taking back to Vygotsky category, so the heart is just geomotives, the Krasnovik's category of geomotives, and this is weight 0. But weight 1, say, or weight -1. Can you?
So if weight exactly 1, you should just shift.
Exactly 1 is
just shift Chow motives by 1.
By 0.
No, shift in the triangulated sense.
Triangulated sense.
shift. So weight 1, you should shift by by 1. By 1 in square brackets.
Okay.
And so also you can also define weight exactly 2, exactly 3, and you want if you want everything of positive weight, then you should consider the smallest subcategory subset of objects containing all of these ones shifts and close with respect to, you may say, extensions.
Yeah.
Do you understand what this?
Yeah.
So this is quite easy. This is the construction. It's quite easy. Yes. So I could say 2 things here. Yes. So there is also analog of this thing for relative motives. So there is also definition of Chow motives, and starting from this you can define it similarly. And yes. So again, this is the case when you can prove something for motives without any new geometry. So there is no clever geometry in this definition, I would confess. So it's quite easy, and you can do something with it. So this is the point. So for this weight structure corresponding to stupid truncations of complexes, yes, minor observation that the heart is not necessarily A itself, but it will actually this is a cubization of A inside this regulated category. It can be a little bigger when if A is not Karobi closed itself, then maybe you will get some new objects in the heart.
So for motives, smooth projective have weight 0, right? Smooth projective arrays have weight 0.
Motives smooth projective arrays you have weight 0.
Can it have this, like if it's smooth and it's weight positive?
Yes.
It's weight negative.
Yes, yes, you are quite right, up to a sign at least. Yeah, I should. So what is the sign?
No, yeah, never mind the sign.
Yeah, so in this convention, the projectives are positive. Yes, and
Since you are the author,
yes. So, but I would like to fix the sign at some moment. So in this convention, I think that the projectives will be negative and the smooth will be positive. And in fact, so if you consider relative motives, so consider motives over arbitrary basis, then there are some properties of weight exactness, left and right weight exactness for base change functors. So there are formalism of at least 4 functors. So f upper star, f lower star, f upper streak, f lower streak, and there are some properties of weight exactness. So these things behave have very reasonable properties. That you may say that these properties lift those of weights of cohomology. So this is the idea.
The take twist doesn't change the weight, right? Tensor with
so if you wanted to remain inside of Chow motives, you should twist by 1 by 1, 2. Yes, this doesn't change with the weight certainly. Actually, twisting by any Chow motives also doesn't change weights for this case. Okay, now so I will tell more. So in the beginning, I told you that non-commutative localizations can be computed using category of homocopy category of complexes, and final result is that actually this is not the only possibility. You can check just any category with weight structure that will have your heart. Will have A inside the heart, and when you localize by cones of morphisms, you obtain in this localization you also have a weight structure, so compatible with the one for C. and its heart will be more or less almost the additive localization by S. So the heart of the new category is calculated in terms of the heart of the old one. You don't need any high information about this triangulated category. What?
One more silly question is take smooth projective curve and eliminate one point. So take so the motive, the Vygotsky motive of an affine curve, smooth affine curve.
Okay.
What will be it will belong to weight 0 or weight?
So to weight. So two consecutive. I already forgot the answer to your question. So I would see 0 minus 1 between. It will have between weights and 0 and minus 1.
And if I eliminate, say, maybe a point of a smooth projective surface, then I will be between 0 and minus 2.
Yes.
And so on. Okay.
Oh, no. It will also be 0 and minus 1.
But if I eliminate, say, if I take a smooth surface, it can be compactified by two smooth divisor.
Yes, and then it will be between 0 and minus 2.
And minus 2. So this weight structure reflects in this weight geometry.
Yes, sure.
Okay, this is the geometry.
Yes, but I didn't use any geometry when I proved these things.
But you have an intuition about what you are doing.
Yeah. So this is. So it reflects geometry, and certainly it even more reflects weights for the cohomology, and I will tell you about this a little if I have some time. Okay, so this is the result. So you have a weight structure for this localization, and you can compute. You have this nice formula for the heart. And in particular, again, so the heart of C will be negative in E. So this is one of the consequences, and also yes, this is one of the fossil formulas, but you will soon see some more formulas for morphisms groups that are not zero. You also have some methods for computing them. Okay, now we come to computations. Okay, I don't want you to remember all these formulas. I just want you to look at them, and so that you know that they exist. And you would also know that it can be successfully written down by a second grade student. So if you compare with the theory of non-commutative localizations, so certain similar formulas were also written down by Gerasimov and Malcolmson. So, so in both of these papers, so they just said we take something for in order to construct the non-commutative localization of a ring, we consider some elements and consider some equivalent some relations on them, and then we prove that it works. So it seems that somebody told them the answer, and after that they with some strange computations they proved that this is really the correct answer. So at least their papers give no reason why the answer should be like this. On the other hand, when you work with complexes and use the yoga of weight structures, so it's you just compute everything in a very natural way. So you just look at the proof as a general statement and just do the steps that you needed in the proof explicitly. And so when you do this, you understand, okay, so we don't have, in order to obtain a nice formula, you should consider something that is called the multiplicative closure of S. Okay, certainly. So it's just a closure of columns of S with respect to extensions in the category of complexes. Okay, so again, this is the first thing that has this virtual natural is in this strangulated context, but has no, I don't know of any explanation if you just work with additive categories. So it turns out, okay, and quite the fact that it was quite amazing to me. So as I've said, so when you have ORA conditions, then certainly your area morphism in your the localization is a fraction. But for general localizations, you can have zigzags of arbitrary long that are arbitrarily long. And it turns out that in this additive setting, you just need a three-term decomposition. And you even can assume that I is just a co-retraction. So it's you don't need much more than fractions. So just a little more than fractions, and you obtain more morphisms as localizations. Okay, and so this any morphism in localization can be presented in this form. And so now the question is how to do the basic operations with morphisms in this form. So here are the formulas. So okay, this is certainly the formula, very easy formula for the direct sum. Certainly, okay, for composition, okay, a little worse, but also quite okay, and also very natural in the correlated setting. Again, we obtain some extension of complexes. Yes. This is mostly his contribution, and I only was telling them do it. So I inspired him, but he did it really. Okay, so when you have the form for direct sum, you can certainly add morphisms, and there is also a formula that is quite nasty. So we have a presentation of morphisms, but certainly it's not unique. So the question is, when you have two morphisms, you can subtract them using this formula, but the question is whether the result is zero. And in order to check whether it's zero, you need you need to solve certain equations. You may say so.
One moment. These formulas are for f written in the form of triples when E is not required to be a contraction.
So there is some flexibility in this result. You may say so. So we can assume that I is a contraction, but this is not necessary, and we can compare them. Okay, and so yes, for example, you can apply these formulas to birational motives. I wouldn't say that it makes me very happy, but at least you obtain some new formulas that again you obtain some new results about motives that were not known previously. Another question is whether they are very useful. I don't know. Not at the moment. Maybe they will be useful later. Oh yes, so I wrote this down explicitly. So you consider, so you can compute them in this case like this, or as I have said, commutative invariance is not really needed, and you can forget about it here. So obtain that morphisms of there are no extensions of positive degrees between birational motives of smooth schemes over U, for example, and also some nasty, okay, moral, maybe not very pleasant formulas for morphisms of degree zero.
The first property is there are not positive degree extensions
between birational motives of smooth U schemes.
For smooth, say even fields over a perfect field.
Yes, so smooth varieties then. So you may say that the idea, so if you consider ordinary motives, this result is true for projective varieties over a field. And since this is Yes. So this when we consider birational motives, this becomes true for all smooth varieties, and we don't need a smooth compactification. We don't need resolution of singularities. We don't need anything complicated at all, as I've said. Just some piece of abstract nonsense, and you get all these results. So you can compute certain part of this category of birational motives. You have some formulas. So another thing is you have some weight complexes, conservative and exact functor of triangulated categories. Okay, now.
If U is just point, means speck of field.
Yes.
Then what is the left hand side? What is better say the right hand side?
Which one? Where?
Yeah.
Here. The right hand side. So the homotopic category of additive, you may say, additive birational motives. Okay. So there are also some formulas for this category. Okay, at least in this case, there are more reasonable formulas from this category than those that are given by abstract nonsense, and you can find them in Kahn's preprint. So I cannot. So I can find them in my computer, but I don't remember them by heart. So it's something quite reasonable, but. Not that easy to remember. Conservative means that this functor does not kill non-zero objects. So they are certainly not isomorphic, but still the connected functor doesn't kill any objects that are not zero. Okay, so yes, now I would like to confess that I'm not sure really that we obtained these results are really very interesting for motives. So as I've said, the most interesting case is the case of motives over perfect field. And this case was already more or less well understood before we started writing this paper. So there are some motives. So if you use some geometry, some results of Voevodsky that are really not very easy to prove, yes, then you can prove it. So the possible methods, so this was proved by Kahn and Sujat in their preprint. And another method is to, oh yes, not much time left. Yes, okay. So you may say, so I may say some remark. Where is it? I don't know where is it. Okay, so for this I will say it without slides. So it was so for example, when you consider category with base structure and you localize it by some category, if you want to the localization to have a compatible base structure, you need this compatible T structure. Then you need this T structure so it can be ограничен.
Consistent. Just consistent.
Ограничить. That can be restricted to the subcategory that you kill. And the funny thing that is no longer necessary for weight structures. So if you localize C by triangulated D, you don't need your weight structure to restrict to D. It's sufficient to have something weaker than a weight structure for D. Okay, so but still, so for effective motives, there are you may say two weight structures. I call them the Chow and the Gersten ones, and so you need certainly more algebraic geometry to prove their existence. So for the first one, the heart consists of motives of smooth generated by motives of smooth projective varieties. And for the second one, you need some larger category of comotives, and then the heart is generated by comotives of function fields over your base field. So this category, so this is more difficult to prove the existence of these Vx structures, and you need some restrictions on the coefficients and on the base field. But after that, your bidirectional motives, you may say this is a pure localization. So you just you localize if you go from effective motives directly. Start with effective motives, then you localize by subcategory where you can restrict your weight structure, either the Chow one or the Gersten one. And so this is another method for proving the existence of the bidirectional weight structure in this is the case when the base is a perfect field. Okay, so. But in this case, you really need much more algebraic geometrical input. Okay, so I just have very few minutes. So I will, as I promised you, I will tell you about the relation between weight structures and Deline's weights. So I did it this time. I think I explained, told this several times. To some of you, but not this time, that when you have weight structure for your C, then for any homological H, so this weight structure will give you a machine. Yes, for computing certain filtration on this cohomology, and also spectral sequence. For example, in the case of the Chow weight structure, it relates the cohomology H of a motive in terms of. You may say there is also the weight complex functor, okay, from dm to kb of Chow, and so the spectral sequence starts from the cohomology of the terms of this complex. So you start with cohomology smooth projective varieties. And you have an spectral sequence that converges to the cohomology of motives. And this spectral sequence will be canonical and functorial starting from E2. This is true for any cohomology theory. Now, Deline's method is that when your H is étale or singular cohomology, okay, then in order to construct his spectral sequence, you need some compactifications. And also, if your M is not smooth, you need some hyper coverings. Okay, in any case, so yes, you write the spectral sequence, and you can write it. Okay, you can write it for any theory that satisfies certain restrictions. For example, theories like this. But then you have the question: if you have two distinct compactifications or proper hypercovers, what is the relation between spectral sequences? And also, even more when you have two distinct varieties. Okay, so, and Deline proved that they are functorial, so because any two can be, for any two compactifications, there is a third one dominating them. And so it suffices to compute like this, to compare them like this. And then, in order to prove something, so he noted that due to weight, this weight sinks action Frobenius. So since the action Frobenius have fixed eigenvalues, it means that distinct. You may say that distinct weights cannot mix with each other. There are no morphisms between of cohomology with distinct weight. And this means that the spectral sequence generates at the E2 term. In E2. And also, and so it gives the filtration doesn't depend on choices. And the factors of this filtration are exactly the E2 of your spectral sequences. And then you prove that anything canonical. So this is certainly very important results, but they break down completely if you don't have generation at E2. For example, for motivic homologies, there's no reason why this thing should generate at E2. And so my method of producing weight spectral sequences is much more general. For example, it can be applied to Connivaux spectral sequences when we don't have any generation results. Yes, unfortunately, maybe they're not, okay, the corresponding filtrations maybe not that useful because we don't have the strictness property. So it's nice to know that weights do not mix after all. But this is a vast generalization, yes, to a very large class of triangulated categories and weight structure for them. Okay, thank you very much. I hope.